This video is about creating a stable IoT system with the ESP32 and Python. We will cover converting raw sensor readings to accurate digital data and handling errors in your code. Real-world data is often noisy. A stable IoT system requires processes for data ingestion, refinement through filtering and calibration, and application to output clean, reliable digital data. Sensors can be digital or analog. Digital sensors like the DS18B20 output discrete data, while analog sensors like soil moisture sensors output a continuous voltage, requiring an analog to digital converter, ADC. The ADC acts as a bridge between the physical and digital worlds. It converts the continuous analog voltage signal from the sensor into discrete digital values that the microcontroller can process. The 12-bit resolution of the ESP32 ADC means it can divide the voltage range, 0 to 3.3 volts, into 4,096 steps, resulting in digital values from 0 to 4,095. To make the raw ADC values, 0 to 4,095, meaningful, we use a mathematical technique called mapping. This converts the raw values into a usable percentage, like 0 to 100%, for easier interpretation and control. Reading a sensor value just once can be dangerous due to noise in the analog signal. This single reading might be highly inaccurate, leading to system errors, such as watering soil that is already wet. We can eliminate noise without changing the hardware by using a mathematical approach like the moving average. Reading the sensor multiple times and averaging the results provides a much more stable and accurate data input. To prevent system crashes when a sensor disconnects, we use error handling structures like try, except. If an error occurs in the try block, the program gracefully executes the except block, allowing the system to continue running. Step 1. Hardware setup. We import necessary modules and initialize the ADC pin. We also set the attenuation to 11 dB, so the ESP32 can read the full voltage range up to 3.3 volts from the soil sensor. Step 2. Data smoothing. We define a function using a try.except block for error handling. Inside, a loop reads the sensor 10 times to calculate a moving average, smoothing out the noise. Step 3. Execution loop. The main loop continuously calls the moisture function. If a valid moisture percentage is returned, it prints the value. This stabilized system is reliable for 24/7 operation. A stable IoT system requires 3 components: hardware, ADC for analog to digital conversion, mathematics, moving average for stabilization, and logic, try except for fault tolerance. Now let's check your understanding. Consider these 5 statements related to building a stable IoT farm system. Here are the answers and explanations. The ADC converts analog voltage to digital. 12-bit resolution gives 4,096 levels. Moving average is needed for analog noise, and try except is key to error handling. The one-wire module is only for digital one-wire sensors.